Hi everyone, this is Professor M. Science, and today I want to discuss one-body operators in second quantization in another one of our videos on rigorous quantum mechanics. We have already learned how to write states in second quantized form using creation and annihilation operators. The next thing we have to do is to look at operators, and today we're going to look at the simplest possible case, one-body operators that only act on one particle at a time. These one-body operators include important examples such as the position or the momentum of a particle. The main goal of the video is to demonstrate the mathematical form of one-body operators in second quantization. But we'll also explore what this mathematical form means conceptually, and although at first it may look a little bit obscure, we'll see it makes perfect sense. So let's go! To introduce how to write general operators using second quantization, in this video I will discuss the simplest possible case, one-body operators. We start with a single particle state space VQ and an operator F that acts on this space. We know from the video on tensor product spaces that we can build a general n-particle state space V by calculating the tensor product over all single particle state spaces. The operator F promotes to this when it acts on the full state space V. To make our life easier, we usually use the simplified notation FQ, where we omit the identity operators of all the other n-1 spaces making up the full state space. Operators like F here, that only act on one particle at a time, include well-known examples such as the position or momentum of a particle. For a system of n identical particles, we know that exchanging any two particles leads to exactly the same physics, so that our state space is no longer V, but instead the subspace of V spanned by totally symmetric states when we have bosons, or totally antisymmetric states when we have fermions. In a similar fashion, the operators that act on a system of identical particles must stay the same when we exchange any two particles, which means that we must work with totally symmetric operators on the particle exchange. In the case we're looking at today, of operators that act only on one particle at a time, we obtain the symmetric operator capital F by simply summing over all the individual operators. And as the sum is over all q from 1 to n, then the action of the symmetric operator doesn't change when we exchange two identical particles. An operator like F here acts on all n particles. However, it is made of individual operators that only act on one particle at a time, and an operator like this is typically called a one-body operator. So how do we work with one-body operators like F? We know that for practical calculations, what we need are the matrix elements of this operator with respect to a set of basis states, and I can schematically represent it like this. Now, as you may suspect, evaluating this expression can be extremely tedious if we have many particles. Remember from the video on the symmetrization postulate that we build totally symmetric and antisymmetric states by applying the symmetrizer or antisymmetrizer to the corresponding tensor product state. The application of the symmetrizer or antisymmetrizer results in n factorial terms to ensure the correct symmetry on the particle exchange. And what this means for the matrix elements of F is that we get n factorial terms from the bra, then the F operator is given by this sum over q, which gives another n terms, and then we get another n factorial terms from the ket. This combines to a huge number of terms, making the calculations very long. In the videos on creation and annihilation operators, we have already seen that we can write the symmetric and antisymmetric state in a highly compact form that gets rid of these n factorial terms. This is accomplished using the second quantization language, where all subtleties associated with the symmetries of particle exchange are captured by the commutator or anticommutator algebras of creation and annihilation operators. Today we want to take this one step further and also write the operator F in second quantization. The key point of this video is that because we're working with identical particles, we can find a much more compact representation for a one-body operator like F when we work in second quantization. To see this, let's start with a basis U in a single particle state space VQ. From the video on representations, we know that the operator F is equal to the sum over KL of FKL and the outer product of UK with UL, where FKL is the matrix element of F in the U basis. To promote this operator to act on the full tensor product state space of n particles, we get FQ equals sum over KL, FKL, and then the outer product of UK and UL, but now we specify the subindices Q to indicate the single particle state space associated with these basis states. The matrix element is given by this, where we again specify the Q subindices of the basis states, but because we work with identical particles, any Q will give the same matrix element, so on the left-hand side we don't actually need to specify the Q index. The symmetrized one-body operator capital F that acts on the system of identical particles is given by the sum over the n single particle operators. And we can now replace this expression here for f of q into this sum, and we can rewrite the symmetrized f operator like this. For convenience later on, we can move the sum over Q inside the sum over KL, and we get this final rearranged expression. This is the symmetrized operator written down in the first quantization language with the sum over the n particles here. What I'll do in the rest of the video is to show how we can write this one-body operator f in second quantized form. The result is actually very simple, and in second quantization we can write f as equal to sum over KL of the single particle matrix elements fKL, and then the creation operator associated with single particle state K, and the annihilation operator associated with single particle state L. Note that I am replacing a UK dagger and a UK by AK dagger and AK, like we have done a few times before to simplify notation. And all that happened is that we implicitly understand that we're always working with the same basis U. Another important point to note is that I have used the letter A to write down the creation and annihilation operators, which we typically use for bosons. But in fact, this expression is valid for both bosons and fermions. All you have to do is to use the corresponding creation and annihilation operators. So what have we accomplished? Comparing these two expressions for the operator, the sum over the n particles that we have in first quantization is no longer there in second quantization. Instead, just like in the case of states, all the subtleties associated with the symmetry of the operator arising when we exchange two identical particles are captured by the corresponding commutation or anti-commutation algebras of the creation and annihilation operators. So how can we understand this second quantization form from a conceptual point of view? Remember that an operator O is a mathematical object that acts on an initial state psi and gives a new state psi prime. Every term of this operator is doing precisely this. It takes an initial ket and then removes one particle in state L, and that's one particle in state K. Put another way, it moves a particle from state L to state K. The rest of the video is dedicated to prove that these two expressions for f are indeed equivalent. The proof is rather mathematical, so if all you want is the answer, feel free to stop here. However, if you're like me and like to see where things really come from, you should definitely join me in the derivation. To get started, here at the top I am simply copying the last expression we got for the operator. The strategy we will follow is simple. We will investigate the action of this operator on a Fock state, and then from it deduce how to write the operator in second quantized form. To do that, let's start by considering a Fock state written as usual in the occupation number representation. Remember that we're using the convention of only writing the occupation numbers of the states which are occupied, so in this case we have that the single particle state ui is occupied ni times, uj nj times, and so on. In first quantization, we can write the state as this normalization constant, then the symmetrizer or anti-symmetrizer depending on whether we have bosons or fermions, and then a tensor product of single particle states, which in principle we can order in an arbitrary way, but which for convenience we group according to the single particle state label. Of course, we could use any permutation of this sequence and we would get the same occupation number state. For bosons, the occupation numbers n can take any positive integer value, whereas for fermions, we can only have a maximum of one particle per state, so n is equal to 0 or 1. As we just discussed, our strategy will be to look at the action of f on this general state, and we start by looking only at the part of f that involves the sum over q. We first copy this part of f, and then act on the Fock state spelled out in terms of the prefactor, the symmetrizer or anti-symmetrizer, and then the tensor product. We have seen that this operator is symmetric with respect to exchange of particles because the sum runs over all n particles. We know from the video on symmetric and antisymmetric states that such a symmetric operator, which here I write as OS for simplicity, commutes with all the permutation operators P alpha. In turn, as the symmetrizer and antisymmetrizer are simply given by sums of the permutation operators, then such a symmetric operator will also commute with S plus minus. This means that we can move the prefactor and the S projectors to the beginning of this expression, and we get the same reordered expression with the prefactor first, then the symmetrizer or antisymmetrizer, then the part of the one-body operator we're working with, and then the tensor product of single particle states. We're next going to focus on this term here, and bring back the prefactor and S operators only later on. Here I have copied this last term we will focus on for the time being, and note that I have specifically introduced the state Q in the sequence of single particle states because we now want to see what is the action of this operator in subspace Q. This sum runs over all n terms, so let's spell them out. In the first line I write the term which acts on the single particle state associated with state space V1. It corresponds to the Q equals 1 term in the sum, so the UK-UL outer product is acting on the first particle here. The second line is the term in the sum acting on the single particle state associated with V2, and it corresponds to Q equals 2, so that the UK-UL outer product is acting on the second particle. And then a general term gives us the action of the operator on the single particle state associated with VQ, and corresponds to the qth line, and so on. Each line corresponds to a term in the sum over Q, so there are a total of n lines. The U states form an orthonormal basis, so that this term here is delta Li, this term here is delta Li, and in general this term here is delta Lm. Each line has one of these Kronecker delta functions, all having L as the first index and then another index as the second one. As a consequence, many of these lines will vanish. So how many lines will be left? As the operator we're acting with up here is acting with the UL term, then the Kronecker delta will not vanish for as many lines as we have UL terms in this sequence. The number of times the UL term appears in the sequence is precisely the occupation number NL. So of all these n terms, a total of NL terms will be non-zero. So what does this mean for the action of this operator on this tensor product? We start with this tensor product term, then act with this outer product in the Q space, and turn it into this term. And this is true as long as m equals L. If m isn't equal to L, then we get 0. Overall, we get NL terms with m equal to L, and in each of these terms one of the UL entries is transformed into a UK entry, while all other U's are left the same. And all these NL terms that we get are simply permutations of each other. So we're now ready to recover the full expression with the prefactor, the symmetrizer or antisymmetrizer, the sum over Q, which is part of the one-body operator F, and the tensor product over n states. Our discussion tells us that the action of this operator gives NL terms which are equal to each other, and which are made of the prefactor, the symmetrizer or antisymmetrizer, and then this new sequence of states in which one UL state from the original sequence has been replaced by a UK state. We can pick any UL state in the original sequence and replace it by a UK in this second line, because all the NL terms are simply permutations of each other, which give the same result under the action of the symmetrizer or antisymmetrizer. Okay, so we've just gone through quite a few manipulations that on a first view may come as a little confusing to follow, but don't worry too much about the details. You can always go back to revisit them in the future. What is important to understand is the general idea of what we're doing, so this is a good point to recap our strategy. We started with a symmetric one-body operator F, and our objective is to write it down in second quantized form using creation and annihilation operators. To do that, we investigate how it acts on a Fock state, and the first step is to write the one-body operator F in the U basis. In the past few slides, we have then focused on just one part of the F operator, the sum over Q here. What we have seen is how this acts on the Fock state written down in terms of a symmetrized or antisymmetrized tensor product, and the final result we just got is the one written down here. So what does this result tell us about the action of the operator on a Fock state? The operator simply picks a particle in state UL in the original tensor product and replaces it by a particle in state UK here. As there are NL particles in state UL in the original sequence, then of the total capital N terms in this sum, only NL of them can perform this action, introducing the factor of NL here. And this is actually all there is to it. This very long maths we just did leads to this very simple statement. The final thing we have to do to figure out how to write the operator in second quantized form is to write this result not in terms of the symmetrized and antisymmetrized tensor products, but in terms of the occupation number representation. To do this for the left-hand side is actually trivial, because this collection of terms here already have the correct prefactors to form the starting state in the occupation number representation. The right-hand side is a little trickier, because these prefactors don't exactly combine to give a state in the occupation number representation. All we can really say about the right-hand side is that it is proportional to a new Fock state, which in fact is the same as the original state, apart from the fact that we have removed one particle in state UL and created one in state UK. So all we have really left to do is to get the correct proportionality constant here. What I have up here is a copy of the latest expression we have obtained, where I have already written the left-hand side in the occupation number representation, but left the right-hand side still as a symmetrized or antisymmetrized tensor product. What we just argued is that this term is proportional to a Fock state, and all we need to figure out now is the proportionality constant. To write down this new Fock state, I have labeled the occupation numbers with n primes to make sure that we distinguish it from the original Fock state where the occupation numbers are labeled by n. Our discussion has taught us that this new Fock state has one fewer particle in state UL, so NL prime is equal to NL minus 1, and one extra particle in state UK, so NK prime is equal to NK plus 1. All other states have the same occupations, so n prime equals n for the rest. Also note that this prefactor here comes from the original state, so it is not in terms of n primes, but in terms of the original n's. By the definition of a Fock state in the occupation number representation, we can write the new state as equal to this prefactor, then the symmetrizer or antisymmetrizer, and then the corresponding tensor product state. We can rearrange this expression by moving the prefactor to divide the other side, and we get the symmetrized or anti-symmetrized tensor product state as equal to this prefactor multiplying the Fock state in the occupation number representation. The left-hand side here is now equal to this term up here, so that we can rewrite the top line by first repeating the action of the operator on the initial Fock state, and then setting it equal to the original prefactor, multiplying this new expression we just got for the symmetrized or anti-symmetrized tensor product. In this final expression, the capital N factorial cancel, and most of the little n factorial terms also cancel with most of the little n prime factorial terms because n prime is equal to n for most terms. We can therefore write this as equal to nl, and then from the two square roots we only have contributions for the terms for which n prime differs from n. One of these terms is nk plus 1, which we get in the numerator because the nk prime term up here is equal to nk plus 1, and the other term is an nl in the denominator because in this case the nl prime term up here is equal to nl minus 1. We then complete the expression with the Fock state, and combining the prefactors we get square root of nl times nk plus 1, and then we write the Fock state in terms of the original n occupation numbers. In this new Fock state, all n's are the same as the original ones, apart from nl which goes to nl minus 1, and nk which goes to nk plus 1. We're almost done. Up here I have the latest result we obtained, relating the action of this operator on the original Fock state, and then obtaining this prefactor multiplying the new Fock state, in which we have removed one particle in a state nl and added a particle in a state nk. From the videos on creation and annihilation operators, we know that ak dagger al acting on a Fock state gives square root of nl times square root of nk plus 1, and then the Fock state in which we have annihilated a particle in state L and created a particle in state K. Comparing these two expressions, we can straight away identify the sum over Q of the outer products of the U bases as equal to ak dagger al. This is the main result of this video, and I want to make 2 points about it. First, I want to emphasize again that I am using the letter A for the creation and annihilation operators, which we typically use for bosons, but this expression is valid for both bosons and fermions. You simply have to use the corresponding creation and annihilation operators with the corresponding commutator or anti-commutator algebras. Second, this expression now makes it very clear what we accomplish by moving to second quantization. On the left-hand side, we have a sum over n particles, which is necessary to make the action of the operator be that of a symmetric operator that doesn't change when we exchange any two particles. On the right-hand side, we no longer have a sum over n. All the subtleties associated with the symmetry of the state are captured by the commutator or anti-commutator algebras of the creation and annihilation operators. To finish, we bring back the complete one-body operator f as equal to the sum over kl of fkl, and then the sum over q of the outer product of uk and ul, and using this result we can rewrite it in second quantized form as the sum over kl of fkl ak dagger al. Yay, we're done! This is the one-body operator in second quantization I wrote down at the beginning of the video, and this form is valid for both bosons and fermions. So how can we conceptually understand what the operator does? It essentially moves one particle from state L to state K, and the matrix element here tells us the amplitude associated with this transition. To gain further intuition about what the operator does when written in the second quantized language, we're going to write down the operator in the basis of its own eigenstates. To do that, consider the eigenvalue equation for the single particle operator f. The V form an orthonormal basis of a state space, and the matrix elements of f in this basis are explicitly written like this. Then for f acting on VL, we can use the eigenvalue equation, and we get this. Before we move on, just remember that the basis is orthonormal, so this is equal to delta KL. Let's now consider the full symmetric operator f of the n-particle system, which we write like this in second quantized form. Here we assume that we're working in the V basis of eigenstates of the F operator, so the creation and annihilation operators refer to this basis. We can now rewrite this expression using the form of the matrix element we just found when working in the V basis. The double sum becomes a single sum thanks to the delta function, so that we get this. Remember that ak dagger ak is simply the occupation number operator, so we finally get this. So what does this mean? In the basis of eigenstates of F, the one-body operator in second quantized form acts in a very transparent way. It simply counts how many particles we have, and then for each particle it adds the eigenvalue of the operator corresponding to the single particle state that that particle occupies. One-body operators, written in second quantization, have a particularly simple form. You should next check out the video on how to write two-body operators. If you liked the video or would like to send me suggestions for future videos, please subscribe.